Anyway, so about a year ago, beginning of last year, the idea was tabled at Knowledge Tree, a document management system based out of South Africa, to kind of launch Knowledge Tree as a software as a service and run it entirely within Amazon's EC2 or using AWS only, so within Amazon using S3, etc. Initially, when I heard this and thought about this, I kind of thought this is actually a pretty dumb idea. Actually, I felt a little bit, I think, like what that dog over there must be feeling right now. Kind of like something is going to go wrong, and when it does go wrong, it's not going to be pretty. Anyway, so Knowledge Tree, as I said, is a document management system. So there were at least some aspects that didn't quite make this some insane project. So obviously, being a document management system, Knowledge Tree does manage documents by its nature. So documents, and documents being essentially discrete objects of data, using an object data store like S3 seemed to be a really good fit. Also the fact that we could grow our data store without having to worry about planning, forward planning, getting more space, when we're going to run out, how fast it's going to increase, really looked like a good idea, and the price at which S3 was being offered also looked good. It's also not an LTP system, which is also great. I mean, we're not having frequent and high volume updates kind of hitting our database, which obviously was going to be the biggest problem. So that kind of also got us thinking, okay, no, it's definitely something we can do around here. So thinking a little bit more about the persistence challenge, essentially we broke it down to 3 different categories of data that we needed to persist. Configuration data, the state of the system after an instance has been booted, and also the user data, obviously consisting of documents and databases. Configuration data was obviously by far the easiest. I mean, configuration management systems have been around for a long time. They're good at handling this, and sort of configuring running servers. And no matter what we were going to do, what platform we were going to use, we were certainly going to have to implement some form. Most probably, we want to keep our sanity, implement some kind of configuration management system. So there's nothing really, nothing sort of going to get us going too much. There was one little hook, is that we do have some configuration that isn't neatly kept within a configuration management system, which was the configuration files that each account would require for Knowledge Tree to be set up for that account in EC2. These are essentially just flat text files containing details of database connections, etc., 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 that are unique to each account. Being flat text files, though, again, S3 lent itself very well to kind of, as an account is created, flat text files get created, put in S3, and sync to the servers from there. Obviously, as a new server is booted up, it simply just syncs everything from there. So the configuration data really not an issue for us. The system state was really a problem around keeping the consistency between the live instances as they're running and the static images as they are stored on Amazon. So a little bit of background here for those who are not too familiar with Amazon. Instances is Amazonian speak for your running server, and you boot up the instance using an Amazon machine image, which is essentially just a Zen.u guest image that's stored on S3 and registered with EC2. So using traditional backup utilities was not going to help us here in the way that traditional configuration management systems were going to help us. So we were kind of thinking and looking around, what are we going to do, where are we going to go with this? And eventually where we got to is, why don't we just go with software appliances? They really seem like a good fit with the cloud. You've got specialized machines, so specialized to a task. You can bring up and tear down machines very quickly. So having specialized machines that just need to perform a very specific function seemed like a really good idea. Also, because they're so specialized, the amount of packages, just the complexity of the system itself is kept to a minimum. So the amount of updates, security patches you need to roll out are kept to a minimum too. Obviously, there is a little bit, I mean, we could also just every time there's a new update, just create an image, bring down the server and bring it back up again. But that also seemed like a lot of work to just roll out one security patch to a whole bunch of machines every time to shut everything down and bring it up, just to kind of have that one security patch propagate through the system. So essentially we decided to go with software appliances and use an application that is developed by RPath, called RBuilder. It's basically a whole package of utilities that provide you the ability to, first of all, define your software appliances, define custom packages for it, include the packages you want in it, and then have it built for you. And simultaneously as building it, or once the build is obviously done, you can push it off to Amazon. To Amazon, it can produce Zen images for you, it can produce VMware images for you, it can produce ISOs for you, just about anything you want. What it also gives you is the appliance platform update service, which allows you to push out the updated packages that you've just created as and when the security fixes come out, and push that out to all your running services as servers. So essentially here we've got a solution with which we could keep our stored AMIs in sync with our running servers. So if we have to bring up a new server, it's not an issue of first having to make sure the latest software is installed or not, or forwards and backwards. So that was just minimizing a little bit the management of the whole cloud. Being able to produce some Zen images also obviously helped with local development. Developers don't always have to go up into the cloud just to quickly test out a few things and try out a few things. So that was the easy part. Next came obviously the user data, consisting of, as I said, databases and documents. So the quick profile of our databases. Each account has its own database. Now, this is not each user account. When you basically subscribe to Industry Live, subscribe to your account, and you can create many users within that account. So we're not crazy enough to think we're going to be creating a database for each and every single user who wants to use the system. But being, by its nature, an on-premise single-tenant application, it did kind of require us to have a separate database for each user. And that does also bring some advantages with it. The database is also a mix of InnoDB and MyASM tables. That obviously brings with it also a certain set of constraints when considering backing up and just in general maintaining the systems. And currently we've got about more or less 1 million tables across all the databases that we need to persist in some other way to S3, which again from a backup point of view does provide certain limitations while you're doing it. So there's certain options that are just not going to be viable. So obviously the first thing you have to do is reduce a single point of failure. And this is where MySQL's replication is exactly what it does. I mean, it's perfect for the situation. So instead of seeing a database as just a single server, we would have database clusters consisting of a single master and replicating back to 2 slaves. So this removed the single point of failure on the database level. The next level where you had a single point of failure was obviously your data center level. Initially when we started off with Monastery Live, you could not determine in which data center your instances were actually going to come up in. Subsequently, with new releases of the EC2 API, you can do that, so you can essentially specify that your master and the 2 slaves are all in separate data centers. So you're even removing the single point of failure at the data center level. Obviously this is not enough, so we still have certain problems to contend with. One is a catastrophic failure in the sense of if all 3 instances die at the same time, or in a quick enough succession that we haven't yet had enough time to bring up a new instance and synchronize it up to the state of the databases that were in the cloud. And the other one is obviously if a master dies and the slaves were out of sync, whatever data was on the master is gone, is to be retrieved. So essentially this lays out our backup requirements that we need. We needed something that could, we needed a system that would back up often and back up fast, that wouldn't interrupt replication, very important, and would minimize redundant data. Because having the backup locally on your instance is great, but it's pretty much useless to us if that instance goes down. So another part of the whole backups obviously consider this has to go over the wire back to S3. Only once on S3 is this backup really complete. So having to push backwards and forwards a whole bunch of data unnecessarily all the time is obviously also going to add, it seems a little bit inefficient solving it that way, and will also increase the time that it will take to for each backup run to complete. And finally also, there's obviously the restore side of things. You want to minimize the time and complexity during the restoration. I mean, if the only time you'll really be using the restore process is if you did have one of the catastrophic failures, you've lost all 3 of your servers, some other way you've got to get the system back up and running as soon as possible. So our solution was brand new, innovative, genius idea of incremental backups and full backups. Never done before. Took me a while to come onto that. And yeah, my boss wasn't very impressed when I came back to him after a few weeks saying, that's my solution. But essentially that was it. So just using incremental and full backups already, you could create, in combination with replication, you could create a fairly well, not absolute persistence, definitely not persistence, but the chances of you losing data could be minimized essentially with our system to roughly about 5 minutes. So you've got a 5-minute window at the worst case of how much data you could lose at any single point in time. So incremental backups, nothing really new there. Conventional way of doing it is just using MySQL's binary logs. It's really fast. You issue a flash log statement, your old log is rotated out. Doesn't take too long. So it definitely fulfills our first requirement, backup fast and backup often. Then you would preferably only want to back up data so no redundant data that's changed. That's the definition of incremental backup, so exactly what you're doing. Any backup has changed, sorry. But there was a problem of the proliferation of binary logs. I mean, if you're going to be backing up the incremental backups once a minute for a whole day, you end up with 1,440 binary logs, which, you know, doing a restore is not only a nightmare, but if anything has gone wrong with any single one of those binary logs kind of along the way, you run quite a big risk of losing most of your backup. It's probably very difficult to fix. So some other way we had to reduce the amount of incremental backups that we taken, and obviously the way to do that is to have a full backup every now and again. So you reduce the amount of incrementals needed between where you are now and from where the last backup was taken. So full backups, again, you've got basically two options there, raw and logical backups. Raw backups using Linux's logical volume manager's snapshotting abilities. Again, gives you very fast, well, very little interruption to replication, which is what we're looking for from a full backup solution. Essentially, what the time that replication is interrupted on the slave is the time that it takes to obtain the locks on the database, take your snapshot, and then release the locks and MySQL continue replicating, and everything is happy always. And then you can basically go back, take a snapshot of your full backup using whichever utilities you prefer, a combination of utilities. We basically decided to settle on using LZO as a compression algorithm because of its speed. It's extremely fast. The trade-off you make with size versus CLIB is marginal compared to the time that it will take with CLIB and then transferring across the network. So we settled on LZO compression for speed. There is, however, a catch with raw backups, which is if something goes wrong with your raw backup, it's almost impossible to fix it up. If there's a corruption in one of the files, etc., you're not really going to be fixing it up. So every now and again, you must probably want to take logical backups, as they are at the end of the day, plain text files that you are able to edit and then persist back as well, and to sort out any problems subsequently as you need to. Now, this obviously doesn't reduce the amount of duplicate data that we're copying every time. Every time you're doing a full backup, now this is the part where I mentioned earlier that we had a combination of InnoDB and MyAsm tables. The problem with InnoDB tables is you can't really back up just an individual database using raw backups. With MyAsm, that's fairly straightforward. You've got a directory that contains everything, is pretty much self-contained. You can back it up, you can move it somewhere else. So essentially, we would then only have to back up the databases that have actually been modified over the last period, be it 10 minutes, be it 3 hours. So it reduced the amount of data we got, but we didn't have that option available to us. So what we decided to do was essentially to specialize our database clusters, or build clusters of databases. We would divide up very infrequently used accounts off onto one cluster. Those are accounts where more often than not we would not have to run a backup every 10 minutes because there wasn't a change happening every 10 minutes. So we were keeping those accounts safe. I mean, once your databases were off on S3, we were happy. It's there. You don't need to be backing it up again. Then, obviously, having a separate one for frequent backups. We also use a separate database cluster up front for initial signups, which is mainly again an InnoDB issue. The InnoDB log just tends to increase and increase and increase. Now you've got trial users coming, signing up for 2 or 3 days, and then leaving off again. You dump the database, but you're still left with the growth in InnoDB log. So this little cluster was basically using the InnoDB file per table, so that when the database is gotten rid of, you don't have extra data still lying around. That's a little bit tricky to kind of get rid of. Next is obviously the backup schedule. So this is again where our 2 slaves helped us. So essentially we're doing a backup, a raw backup every 3 hours, a logical backup once a week, and then slave backups every 10 minutes. But now what we also do is we stagger the 2 slaves. So you've got the 1 slave backing up, for instance, every 10 minutes, starting on the hour, with the next slave starting 10 minutes every 5 minutes past the hour. So this is where we essentially were able to cut our binary logs in half, yet still maintain a 5-minute interval, roughly 5-minute interval, between the backups that we were getting for an emergency case. The same with the full backups. You never really want to have 2 full backups running concurrently. I mean, a full backup could still, even with a raw backup, can still take up to an hour. If you've got 2 full backups running for roughly an hour and they both crash, you're rolling back all the way down to an hour again that you have to restore to, which is kind of defeats the whole point. So having 2 slaves essentially also gave us an option to make sure we never really have 2 full backups running concurrently, so we can really keep our 5-minute paradigm. Now this is also where there's a little bit of a break in it. Obviously while the 1 slave is running, it's not backing up any incremental data back. I mean, while the 1 slave is doing more backups, it's not backing any incremental data back up to S3. So it becomes a 10-minute interval for that period that the full backup is being run. Documents was really the easy part. As I mentioned earlier, you know, they're discrete bits. They're discrete objects, basically, of data, really ideally suited for S3. This is what S3 is good at. And as it so happens, also the most valuable data in a document management system. I mean, there's other data that's also important, otherwise a document management system would essentially just be a web browser where you can access your files through. So there is other important stuff. I mean, there's triggers, there's workflows, there's permissions that can be changed, etc., that you don't want to lose. So there is other important data. But this is most certainly the data that customers would be most upset about losing. We really have to go back to them in a really bad failure and say, listen, I'm sorry, those permissions you configured 5 minutes ago are gone. You know, it's kind of easier to explain. Going back and saying, sorry, those 5 documents you uploaded are gone, will definitely unnerve customers a lot more. So documents, good fit for S3, easy to back up. However, just having a backup of the documents on S3, if we did lose our 5-minute window in MySQL, if we did lose at a 5-minute or even a 10-minute interval of our backups, we wouldn't easily be able to get those documents back into the repository of the document management system, because just knowing there's a document doesn't really tell you where the document belongs to, who it belongs to, where was it structured in the document management system. And this is essentially where the metadata that you can attach to each key that you store on Amazon, so each file that you store on Amazon really came in helpful. You can add some additional information, some additional metadata to each file that we were adding and assisting off to S3, that in case of an emergency recovery, you would be able to recreate where that document actually was and put it back in place. When SimpleDB was later added, we could even extend that and make it more granular and essentially create a journal of what's happening with documents within Knowledge Tree. So it doesn't quite have everything you would need from a document management system, but the main actions of what's happening to the document are journaled often in SimpleDB. So the combination of our 5-minute backups and using sort of the SimpleDB journal pretty much gave us a pretty watertight mechanism to ensure that customers won't lose their document and won't lose most of the context of the document in case of a failure. So the fact that S3 is massively redundant obviously doesn't mean that backups all of a sudden become unnecessary per se. There's still programmer errors, etc., that can happen, both on the side of Amazon and on the side of, and on our side, that mistakenly could delete a whole bunch of documents out of a bucket. So there's still the need to back up those documents off to another bucket. At least that's what we felt for our needs. So essentially what we did is we created a separate Amazon Web Services account that read-only access to a bucket, and that account was essentially used to harvest a queue where new documents were put into, or message about new documents being added, and persisting them off to a separate bucket in case of a program error. So overall, as I said, we've got a very low risk of data loss around user documents and the context of user documents. There is still a loss around permissions, metadata, etc., but nothing too bad. So our experience with S3 over the past just under a year has been that it has been a fairly reliable service. There have been 2 major outages, one ironically just the Sunday as I landed here, which didn't cause us any document loss, but it did cause an impairment of our service in the sense that we couldn't access them quickly anymore, so nor could our customers access their documents. Now, in such a failure, what obviously becomes important is our backups. What do we do with our backups? If we can't persist our backups back to S3, they're kind of again sitting in limbo land, and anything can happen to them, which means we lose more data. So in a case of an S3 failure, what we start doing is we start distributing our backups to our other running instances around, just to distribute the risk. And if the S3 failure lasts too long, essentially what we do is we start pushing up the backups to an external host that does have persistent storage. Also, we do have a caching mechanism for documents that are retrieved from S3 within the cloud. So the most recently used documents, customers will still be able to access on a read-only basis. So in sum, S3, 2 failures lasting a few hours, but nothing that brought us completely to a grinding halt, and was, kind of we could manage it. Finally, EC2 failures are found much less. So we've had hundreds of hosts booted up over the past just short of a year, of which we've had 7 instance failures. Of those 7 instance failures, we've been notified about the failures up to a week beforehand. The shortest period was 48 hours. You essentially get an email from Amazon saying your instance is running on a degraded host, you're only terminating it on such and such date. So essentially really running really well, so no problem. We did however have one lost EC2 instance during the API outage at the end of last year, which was could have become much nastier, because the problem with that outage was not only were instances being terminated randomly, but also you couldn't boot up a new instance to replace your instances. It was just kind of weird coming together of a whole bunch of facts with Amazon. But apart from that, really EC2 has been running fairly solid. So this is obviously all well and good. Anyone who's been following EC2 a little bit will know that persistent storage is on the horizon. I kind of get to hear that is hopefully coming soon. They've been trialing it since early this year. And essentially what the persistent storage gives you is the ability to attach a block device, a raw block device, straight onto your instance, or a few block devices straight onto your instance. And that block device is persistent. Quoting Amazon, it's designed for high throughput and low latency. So this is really, that's probably going to solve all our problems, kind of, and make most of my speech or most of my presentation today pointless. But yeah, the really neat feature about the block devices though is the ability to snapshot whatever is on the block device off to S3. So essentially using a combination of LVM and S3, and the snapshot ability of S3, you can still create documents and recreate database clusters as you need. So yeah, I kind of ran through my presentation out of nervousness a bit. I wanted to say a bit more, but yeah, thank you. And finally, if there are any questions, please go ahead and pop on. Sure.
I think you're overthinking the MySQL backup strategy. You probably just use snapshots in the master and binary logs and slaves. That'll be real-time backup.
Why you say that?
Think about it, okay? Think about it later, okay?
Okay.
On MySQL DBA, that's what I do.
Okay.
So they already have EC Amazon Web Services already has something called mountable storage.
Yeah.
That's not what you're talking about.
That's exactly what I'm talking about. So no, so
That's
yes,
a mountable file
storage.
system, not a
Sorry,
block
so the
device.
question is if you get mountable. Yeah. Sorry, the question is if you get mountable storage with Amazon EC2. So yes, you have got local drives that you can mount, but they're not persistent.
No, they have now. I think that's. I don't know if it's the same, but they have another one.
Oh yes.
Is it?
Yes,
It's
they're
not a
block
device.
devices.
It's a mountable file system.
Exactly.
Remote.
Exactly. So that's the raw block devices. So it's not a file system. You can put whatever file system you want on it. But yeah, it's essentially a raw block device that you can do with whatever you want.
Yes, in selecting archive, have you looked at other provisioning tools or?
We have briefly looked around. So the software appliance methodology is kind of taking off at the moment. Ubuntu is bringing out Juice. Novell is bringing out their own one. But at the point when we were working with this beginning of last year, there wasn't really much noise being made from those vendors about their tools. So we didn't look at that stage. Okay.